Okay, what I want to do here is kind of go through an example of kind of more of a modern power plant design. And this one is obviously a lot more complicated than, just a bit more complicated than the one we did last time with the Rankine, okay? It has 10 different states, okay? It has 2 turbines. It has both reheat and regen, so it's got a lot of stuff in it. But this is getting ourselves pretty close to more of a modern power plant design, okay? And really, we have all the tools we need to do this, okay? There's not a lot that's new here. It's just kind of putting it all together in this kind of problem, okay? It's messier, it takes longer, it's more complicated, yes, but okay. So let me just kind of read through it here so we can kind of point out to it, and then I want us to kind of work through this this problem. All right. So we got a steam power plant that operates on an ideal reheat regen Rankine cycle. Has a net power output of 80 megawatts. Okay, so that's pretty good. You know, that's going to power a pretty good neighborhood, and more than just a pretty good neighborhood. You know, nice area. Okay, a city. You know, steam enters the high pressure turbine at 10 megapascals, 550 degrees Celsius, and leaves at 0.8 megapascals. Okay. Some steam is extracted, and this is where it gets a little bit complicated to follow these lines here. Some steam is extracted from the high-pressure turbine. Let me show you what this is. We've got some steam that goes that way, and some steam that goes that way. I've got a red line and a green line that break up where the steam goes from the high-pressure turbine. The fraction 1 minus y goes toward the boiler, whereas the fraction y goes towards a closed feed water heater. Okay? And the reason we do this is what I explained before. We have regeneration, which essentially takes some of the high pressure turbine output, some of that steam. It's really hot, okay? And we use it to heat up some of the stuff that's coming back in the feedback loop. Basically, what's coming back into the boiler is liquid water, but we want to heat it up a little bit. We want to heat that up. And so what we do is we use a little bit of the turbine output. Okay, now we don't want to use a lot. Y as a number is a fraction between 0 and 1. It would be ridiculous for that number to be very high and close to 1, because then we wouldn't be throwing much through the turbine. We would be extracting, most of it, and we wouldn't be using the low pressure turbine very much. Okay, so you don't want Y. You don't want to extract a lot. Okay, typically maybe 10% or 20%, something like that. So maybe 0.1. Y might be 0.1, 0.2, something like that. Maybe 0.3. Okay, but the rest of it goes through the boiler. Okay, it has a reheat, what we call reheat, and then it goes into a low-pressure turbine. So keep track of the lines there, okay? All right, and then what happens is the rest of the steam is reheated to 500 degrees Celsius and expanded in the low-pressure turbine to the condenser pressure of 10 kPa, okay? Determine the mass flow rate of the steam through the boiler and the thermal efficiency of the cycle. All right, so you look at this and go, oh my gosh, where do I start? All right. The thing you're going to need to do when you do this analysis, you're going to look at this and go, oh my gosh, there's so much stuff here, all right? Remember what I told you before. If you have your enthalpies, if you have your H's, you can pretty much do anything you want, okay? And that's what I want us to think about. So what I'm going to do on the right side here is I'm going to kind of write down H1, H2, H3, H4. I got to go all the way to 10 because there's 10 different states in this problem. H5, H6, H7. I'm going to kind of work my way down here. H8, H9, H10. I have to write it a little bit bigger than what you probably have to on your page, but okay. So you're going to kind of write down all our H's. Now, some of these H's are going to be easy to find. Some of these enthalpies are going to be pretty easy to find. Okay. Does anybody have any of those 1 through 10? Reading the problem, can anybody tell me one of those that we can probably find pretty easily? So what number is that in the picture? 5. Yeah. 5 is going to be easy to find because it says steam enters the high pressure turbine. We know at 5 it's going to be 10 megapascals and 550 degrees Celsius. So that should be pretty easy to look that up in the table. So let me pull out my tables here. That one's going to be pretty easy to do. Okay, I got to get my tables here. And it's going to be steam, 10 megapascals, 550 degrees Celsius. So I'm going superheated. I'm pretty sure it is. Okay, superheated, 10 megapascals, 550 degrees Celsius. That one's going to be pretty easy right there. That's going to be 3502, right? 550 degrees Celsius, 10 megapascals, 3502, okay? So we're going to write that down for H5. H5, we look it up in the tables. 3502, okay, kilojoules. I don't know, did I have a 0.0? Kilojoules per kilogram. You look that up based upon the known information on state 5, which is given in the problem, and I wrote it in blue up there on there just so we all see it. Okay, so that's 1. Okay, I need 10 of them, but I got 1. Okay. Anything else we can see? Oh, did I read it wrong? 550. It's 550. Yeah. Okay. Good. Okay, we got it. Yeah. What's 1? 7. 6. 7. 6 and 7. No, you can. No, 5 and 6. Yes. In fact, that's a good point. What you can do, another one that's pretty easy to find, is state 6. State 6 is what comes out of the high pressure turbine. Okay. Now, when we do this analysis, and it says using ideal Rankine, okay, ideal means that all our turbines are isentropic, and that means S5 equals S6. So when we try to solve for state number 6, we're going to use the fact that S5 equals S6, and by the way, we do know the pressure P6. We know P6 because it is basically, if you read it carefully, if you read the problem carefully, it says that the steam leaves at 0.8 megapascals. So this is going to be 0.8 megapascals. So what you would do is you would look up S5, which, by the way, would be really easy, right, because we already have it. It's 6.7585, right? You would look up S5, 6.7585, and then you would use P6's 0.8 megapascals, and you could solve for H6. I'm going to kind of cut to the chase and just give you the answer, okay, since I don't want to take more time. It turns out it's going to be 2811.9 is a pretty good estimation, kilojoules per kilogram for that one. Okay, so we got that one, all right. But there's other ones we can get, okay. 7 we could get, yeah, because we know it has the same pressure. By the way, 7, it has the same pressure P7 as it is P6, which is that 0.8 megapascals. And if you read the problem carefully, it tells you what T7 is. It tells you what the temperature is going into the low pressure turbine. It heats up a little bit in the boiler, and then it comes back to the low pressure, and it says, if you read it, it's reheated to 500 degrees Celsius. So we have that as well. We have 500 degrees Celsius, 0.8 megapascals for 7, okay? So we got this one as well, okay? And I'll just go to the tables. 0.8 megapascals and 500 degrees Celsius, I believe that's right there. So you get 3481.3. Same S, yeah, you can do the same thing. 3481.3. So this is 3481.3. kilojoules per kilogram. Okay? And 8, by the way, you use the same thing that we just did on the other turbine. When we went on the high pressure turbine, I used the fact that S5 equals S6 because it's isentropic. Well, the low pressure is also isentropic, so you can do this S7 equals S8, and you know the pressure at 8 is very low. It's 10 kilopascals. So, and it turns out, if you do that analysis, I'll just shortcut this for you. It's 2494.4 kilojoules per kilogram. All right. Now, I'm going to stop right there finding H's because there's more. I know there's more. Okay, we could get more. Okay, but what I want to do is I want to start thinking about what we're doing. Okay, I think there's really 2 steps to this problem. Yes, you do need to do all the thermodynamic analysis to get all your H's. Okay, or as many H's as you can get. Sometimes you can't even get all the H's. Okay, I'll just tell you that. Sometimes you can't even get all of them. Okay, sometimes you can, sometimes you can't. In this case, you can't. I'm just going to tell you, we won't be able to find all the H's. Okay, and you say, well, what are we going to do? Well, here's what I want to do. Here's what I want to do. I want us to think a little bit and set up some equations. Okay, so help me out with this. Okay, help me out. I think you guys can do this because we did this last time. Okay, we did this on Tuesday. But I want to see if you can do this again. See if we can do this. I want to do, first off, I want to figure out what is an equation. How can I write an expression for the work out of both turbines? The combined work out of both turbines. Now, before we do that, let's just focus on the high pressure turbine. I want to write an expression for the work out of the high pressure turbine. But here's the deal. Here's how I'm going to simplify. I want you to write this in terms of the H's and in terms of the m dot. So, if you have, how could I write an expression? Let's just pretend we know what the H's are. Just pretend we know all of them. Okay? How can I write an expression for the work output of the high pressure turbine if I knew what all the H's were and I knew what m dot was? So can you give it to me in terms of m dots and H's? Times mass flow times mass flow rate times H6 minus H5. That's super close. Yeah, it's mass flow rate times H5 minus H6 because H5 is greater than H6, and if you'd get a negative number. Now, is that wrong to get a negative number? Not really, but remember when you write the first law, you would write it H6 minus H5 like you said. But you'd have a negative in there. You'd have negative work equals negative. I'm just going to keep things positive. I think it's going to be easier to just keep things positive. So I'm going to write it this way. I'm going to write m dot H5 minus H6. Okay? And I'm going to try to keep everything positive. Okay? Okay, now that's not everything. What about the low pressure turbine? Can someone then, I have to be careful. M dot times what? 1 minus y, yes. Yeah, notice this, yeah. In the low pressure turbine, you have to write m dot times 1 minus y because that's not, all the m dot is not going to the low pressure turbine. Only the fraction 1 minus y is going to the low pressure turbine. Now, then what do I multiply this by?
H7 minus H8.
H7 minus H8. Great. See, this makes things simple. All I have to now do is if I find my H's, I can just plug them all in, right?
Sure. All the H's we need.
Yeah. On this one, we actually do have all the H's we need, yeah. So, but I don't have m dot, right? And I don't have y. All right. So. So, yeah. So, and let me write this. Make sure we know m dot and y are unknown. So that's two unknowns that I'm going to have to solve for. Okay. which means at minimum I'm going to need at least 2 equations. Okay? Now, this equation I just wrote doesn't really help me solve for a new unknown because it introduces another new unknown, namely work out. But that's okay. We can still keep going. Now, yeah. Oh God. So you're saying, and you're almost correct.
Oh wait, but there's the pumps.
Yeah, it's a net power output. You're saying, well, hold on, can't I just set this equal to 80 megawatts? No, you can't, because this is just the output of the turbines. The net power output is the 80 megawatts. So let's figure out now. This should be easy. Everyone can do this, let's hope. I want to get the work input for the system. That's the work out of both turbines. Now we're going to calculate the work. Ooh, this thing doesn't write very well on the left side for me. Work input. Now when I say work in, there's really only 2 places that I'm putting work into the system. Pump 1, pump 2. So let's take a look at pump 1. Can somebody, maybe a new person, maybe somebody else, can someone do this? I think you can. Can somebody give me an expression from H's and M dots and all that good stuff for the work in on pump 1? A new voice. Come on. Challenge somebody. You do it? Almost. You're so close. It's almost that. Think it's not just M dot, because not all the mass is flowing through pump 1. Yes, that's it. Because the only thing that's flowing through pump 1 is M dot times 1 minus Y. So very good. This going through pump 1 is going to be M dot times 1 minus Y times H2 minus H1. Very good. That's the work of, and that Y looks kind of messy. Maybe I can make it look better. 1 minus Y. That's better. Pump 1. Yeah, that's not everything. I got to add pump 2. But pump 1, yeah. Because what's flowing through pump 1 is only what comes out of the low pressure turbine, which is what goes into the low pressure turbine is 1 minus Y fraction of the mass flow. So it's 1 minus Y times mass flow, and that's pump 1. Look at what numbers are on both sides of pump 1, 2 and 1, H2 minus H1. Now, why is it not H1 minus H2? Because remember, the pump increases the energy. So what comes out of a pump has more energy than what comes in. So you have to do H2 minus H1 because what comes out of a pump has more energy than what goes in. Unlike a turbine, it's the opposite. What comes out of a turbine has less energy than what goes in because you're extracting energy from the turbine. Okay? So now, how about pump 2? How about somebody else? Can someone else give me the analysis of pump 2? I think now you've seen the pattern. You should be able to do it. And you know it's going to start with an M dot. Good? Yes. See? You can do this. Excellent. Yeah. So that represents all of the work input.
Why is 3 there?
Because 3 and 10, that's just the way they numbered it. At some point,
Numbered like that, it makes no sense.
well, because they're all being combined, there's really no way to make the numbers all like pretty. Yeah, there's going to be somewhere there's going to be a 3 next to a 10 or a 7 next to a 2 or something. Because of the way it all mixes together on the back end, you can't really do that. Something's going to happen like that. They could have named the 10. They could have made that 4, and then they could have, I guess, done different. I don't know, but they'd have to go back through it and do it differently. So it would have always happened. So. Okay, now the only place in which we transfer heat into this system is at the boiler, right? The boiler has heat input. That's where we burn something. Coal, natural gas, nuclear energy, something gives us heat. Okay? So we gotta have something to give us heat. And it's going to heat up water. That's all we need to do. It's not very complicated. We just heat up water. Now, can somebody, this is a little trickier, but I think you can do it. Can someone help me give me an expression for the Q dot in here? This is a little trickier, but you can follow the same, kind of format we've been doing. And give me an expression for Q dot in. You're going to have a couple of terms here. It's not just one quick thing. You've got two things. You've got to add something to another thing.
I think we can do, we can at least do the m dot with no y's next to it.
Good.
Times the difference between H4 and H5.
Yeah, which would be H5 minus H4, right? Yeah, that's good. That's the main part of the boiler right there. M dot H5 minus H4, and yes, all of the mass flow goes through the boiler. But then what about 6 and 7? We got to add.
Go in there too.
It goes in there too, so plus. Now, how would I write that one? H7 minus H6, that's good. M dot times what?
7.
Well, we in convention, we've been adding the y term. How much of it goes through? 1 minus y, right? And then you do the H7 minus H6. Good. Good, you got it. Right? See, you can do this. See, you do this. These are not too bad. Okay? Now, it's tedious. Oh, this is going to be real tedious when we get all done. I'm giving you something harder than the homework. I know that people don't believe me, but I am. Okay. And then condenser. The condenser is where we lose heat, right? Because the condenser is going to take that stuff coming out of the low pressure turbine and basically turn it into liquid water. And so this is where we're going to have Q out. This is the easiest expression to write of the four. And that is, what is the expression for Q out of the condenser?
Then times the change between H8 and H1.
Yeah, M dot 1 minus Y, H8 minus H1. Very good. Yeah. Okay. Now, I've written a lot of stuff there, but this is going to help us do the analysis. It's going to help us do the analysis here. Because what I've got is I've got an expression that tells me all the work that comes out of the system, an expression that tells me all the work that goes into the system, an expression that tells me all the heat that I have to burn, you know, all the stuff I have to burn, how much heat's going in, and an expression for how much heat's going out. Now, we know, now let's start writing some equations. Now let's do some real analysis.
Is that a 4 on W out or a Y?
There's no 4 anywhere except for Q in. So no, on W out, that's a 1 minus Y. Sorry.
Wait, there's a 4 on Q in?
There's a 4 on Q in, it's H5 minus
Yeah,
H4.
I was looking at W.
Yeah. But on, yeah. Sure.
Is it 1 minus y everywhere except for where it's in y?
Well, yeah, but not 4 and 5. That's just M dot, right? Because at 4 and 5, it all combines together. But on Y, it's at 3 and 10. And then it's 1 minus Y at 6, 7, 8, 1, 2, 9, and 4. Oh, sorry, it's not 4. 6, 7, 8, 1, 2, 9. Yeah. So there's a lot of places where it's 1 minus Y. Yeah. Yeah. It's just a percentage. Yeah.
But the stuff that's coming out of 5, isn't that just...
That's all of it. Everything's through 5. Yeah. And then 6, you're right. 6 really is everything too. Yeah. And then it gets split right at 6. So it's a little confusing because 6 is the point where it splits.
Doesn't part of it lead out to 7 and part of it lead out to 5?
Part of it, 5. It comes in at 5. Part of it splits out to 6, and then goes to the boiler. Part of 6 goes to the boiler. Part of 6 goes to the closed feed water heater. That's what gets a little bit confusing. So
W out is the turbines. And
the W out the turbines. W ins are the pumps. Yep. And I'm glad you brought that up because now it's time to talk about writing a real equation that we're going to use. We know, yeah, these aren't real. These are good. They're going to simplify now. Watch this. Help me with this. We know we produce a net amount of work of 80 megawatts. Now I'm going to help you out. Anytime I see a mega, I like to convert to a kilo because I know pretty much most of our units are going to be in kilowatts. So we really produce 80,000 kilowatts. All right. Now, don't overthink this. Don't overthink this. Express the network out in terms of W out, W in, Q out. Make it as simple as possible. Make it as simple as possible. Some people were before trying to make it more complicated by adding other terms, which could be correct. But what's the simplest expression for net work out?
Just work out minus work in.
Yeah, work out minus work in. That would be the simplest, right? Why would you involve heats when the simplest thing would be work out minus work in? So let's just keep it simple, right? So let's just do that. So this is really equal to W dot out minus W dot in. Okay? Now, I am not going to do this, but I certainly could. Substitute those two expressions for W dot out and W dot in that I've already written down. I could substitute them in here and write a big old equation. But why? We already did it. Right? That's why I'm doing all that, so I can just write that instead of writing all that other stuff. Okay? Does that make sense? Okay? So this is, right here, an equation we're going to use. This equation... hold on. No, this is good. I'm sorry. This equation, there's nothing wrong with it. For a second, I thought I forgot m dot, but m dot's buried in the equation, so we're good. So it's all buried in there, so it's all good. Okay, so this is perfect. That's an equation. I can use it. But turns out I need more than just one equation. Okay, I'm going to tell you this. If you go through the analysis of working through all your h's, some of the h's you're just frankly not going to be able to find. Okay, some of the h's here you're not going to be able to get. I told you you're not going to get them all. Now, I showed you examples of getting H5, H6, H7, and H8. So I got 4 of them, but there's another 6 more, okay? Does anybody want to venture a guess? I'm going to tell you there's 2 of them on there that you're really not going to be able to find without doing analysis. You're not going to be able to find it just straight up from the problem like I did with 5, 6, 7, and 8. 4 is one of them. You really aren't going to be able to find H4 because the only thing you know about state 4 is its pressure. You know the pressure right there is 10 megapascals, but that's all you know. And it's coming out of a mixing chamber, so I don't know. You're not going to be able to get H4. I'll just tell you that. You just don't know enough about it, okay? So that one's going to be a tricky one. You might be able to make some assumptions, and I'll talk about some assumptions later on to simplify things, but frankly, other than making an extra assumption, you really don't know. There's another one in there that you really don't know too well either. 9. Yeah, 9. You really don't know 9 really well either. Okay, it comes out of the closed feed water heater, and I'll talk about that in a moment. You really don't know it as well. You can't really get 9 too easily. I mean, you could again, there's an assumption you can make that would be roughly good. It's not a bad assumption. I'll talk about it at the end. But you really don't know 4 and 9 very well. Now, it turns out you could, if you carefully do the analysis, you can get H1, H2, H3. You can get H10. Okay, you can get the other ones. And yeah, so you can get those, but you really can't get 4 and 9. Okay, so it turns out, here's the deal. It turns out you actually have 4 unknowns in this problem. Remember, we don't know m dot, and we don't know y. We still don't know those 2. We knew we had to get those 2. But it turns out you don't know H4 and you don't know H9. So we actually have 4 unknowns. So that means I'm going to have at minimum 4 equations. And frankly, all I've written right now is 1. You might say, hey, doesn't it look like you've written 5? You've written 5 equations, not just 1. But really, I've only written 1, that box in red, because those other 4 equations have introduced new variables that I don't know what they are either. Okay, and frankly, I don't care straight up what they are. I mean, I do, but not right away. Okay, so I'm going to have to do some more analysis. Now, I got another one for you. If you were to apply, this is going to give us another equation, and see if you can figure this one out. If you could apply the first law of thermodynamics to the entire system here, notice what we have. You have Q in to the boiler, Q out to the condenser, work in on the pumps, work out from the turbines, right? If you were to apply the first law of thermodynamics to the entire system, could you write that in terms of what we already know, just like what we did here in my red boxed equation? What would that look like if I just looked at the whole stinking thing and wrote a first law? What's the first law? Energy in equals energy out. So what would that look like here? See, it's simple. Don't overthink it. What's that? I like it. Q in. Yes, yes. This is another equation. Right? There's nothing wrong with this one. It's basically saying that my work in and plus my heat in equals my heat out plus my work out. Yes. Yes, yes, yes. Now, some of you might say, well, hold on a second here, Dr. Reynolds. This is confusing because normally we have negatives, works, and negative heats, and I'm just putting everything as a positive. That's why I have to add the little subscripts in and out. Okay? So you might, if I didn't have those subscripts, if I didn't have ins and outs, then it'd be much more confusing. But I added the subscripts to make this easier. All right. So I got this one. This turns out to be another equation because it's the first law, right? There's nothing wrong with that. So that's true too. That gives us another equation. Whatever energy is coming in is equal to the energy going out of the system. I'm going to need two more. Any thoughts on how I can grab two more equations to get this done? To get this analysis done here, because these two are great. But I got four unknowns. You don't know that until you go through trying to find all your H's. But it turns out you really don't know two of the H's, so you really have four unknowns, and you got to have four equations. So take a look at this diagram here. Is there any other kind of analyses that you could do here that could give you some more equations? Yeah, people ask me about that. Now, the second law is used between 5 and 6 and 7 and 8 because the turbines are isentropic, right? So the second law is definitely used on the turbines, but I don't think there's anywhere else you can use the second law except for the turbines. Anything else we can look at? It's definitely the first law. Okay, it's definitely the first law. Anywhere else where I can possibly apply the first law and give me another equation somewhere? Any thoughts? It's not an easy question, but I was hoping maybe somebody could go, what if you try this, or what if you try that? No, we already wrote the first law on the whole system, so I really can't look at the whole system anymore. I have to look at individual components now, yeah, because the first law not only applies to the whole system, it also applies to individual components. So are there some individual components in which I could apply potentially the first law? Oh yeah, those definitely has something to do with H9 and H4. So where could I apply the first law? You bring up an interesting point, okay? You're saying, would H9, H10, and H4 be equal to each other? Okay. No, yeah. Okay, let me say this. You make a really good point. That mixing chamber, technically you're wrong. Technically H9, H10, and H4 are not the same, but practically speaking, they're really, really close. Okay? No, because Q in, again, we just introduced another variable Q in. I mean, that's not really going to help us. No, you're going on the right way. Yeah, exactly. What if you did an analysis of the mixing chamber? Let's look at this mixing chamber. What if we said energy in equals energy out on just the mixing chamber? All right? That's what we're doing. All right, let's do it. So I'm going to have to pull down here, go here, but you can look on your page. If you look at just the mixing chamber, Can you give me an expression for the energy that's coming in at 9? What would it be? I'm going to start you out with an m dot. M dot times what is the energy coming in at 9? 1 minus y times what? H9, right? That's what's coming in at 9, is m dot 1 minus y times H9. Now, give me an expression of what's coming in at 10. These are both coming in, so I'm going to add them up. Energy in minus energy out equals 0, or energy in equals energy out. And good. See, this is easy. Okay, so now give me an expression for what's coming out of that thing. M dot H4 is coming out, right? That's it. Equals 0. That gives me a whole nother equation right here. I analyzed the mixing chamber, and it gave me another equation. Now, before I go on, I want to come back to this point of H4, H9, H10. I'll give you, make sure you get a chance to write that down. It does turn out, by the way, that H4 is pretty darn close to H9 and pretty darn close to H10. They are actually really, really close together. Why is that? Well, think about it. They're all pretty much going to be liquid. They're not going to be steam. They're all liquid. They all have to be at the same pressure. Because if you mix stuff together in an open environment, in like a mixing chamber, they pretty much have to be the same pressure. Okay? Because they're all coming together. So they're all the same pressure. They're all liquid. So the only difference that could possibly be between 4, 9, and 10 is slight differences in the temperature. Okay? Now I will tell you this, that one of the assumptions that is sometimes made in mixing chambers like this is if you have all liquids going in, which is mostly what you have, and they're all at the same pressure, which pretty much they have to be, sometimes we'll actually make that assumption. To simplify analysis, we'll actually make the assumption H4 equals H9 equals H10. Okay? That's actually not a bad assumption. It turns out that these are going to be very close together. They're going to be very similar. Technically not the same necessarily because they could be slightly different temperatures, but practically speaking, they're pretty much all the same energy. They're pretty much all the same. Okay? So they're not going to be that much different. But I don't want to just jump to that conclusion. I want to at least write it down and kind of go through the analysis. All right. So now, I need one more equation. Any thoughts? Where am I going to go to get that one more equation? No, that's not really going to do anything because I don't know efficiency. Yes? No, I think what you got to do is we got to look at that, the thing denoted closed feed water heater, closed FWH. We looked at the mixing chamber, right? Why don't we also look at the closed feed water heater, FWH? And why don't we just do the same analysis we just did on the mixing chamber and do it again on the closed feed water heater? That's what you got to do. So here, let's just do it. Okay, here's what we can do. We'll do the same thing. We'll write the energies in and the energies out. We'll write the energies in and we'll subtract the energies out. What's coming in to the closed feed water heater? What comes in on top? How can I write that energy down? M dot Y times what? H6, perfect. What's coming in on the side, the right side? M dot times 1 minus Y, H2, good. What's leaving on the left side at 9? Minus M dot 1 minus Y times H9, right? What leaves on the bottom? Well, this is easy, right? Minus M dot times Y, H3. That has to all go to 0, equals 0. Because the closed feed water heater is also a system that just simply transfers heat between the two tubes. Now, the only difference between the closed feed water heater and the mixer is that the closed feed water heater, the two substances aren't mixing, right? They're both in their own tubes, right? They're not touching each other. but they are transferring heat between each other. That's what the point is, okay? Anyways, it gives us another equation, so you can analyze that as well. Now, some of you may be going, oh my gosh, we got a lot of stuff going on here. We got 4 equations, we got 4 unknowns, but we got actually a bunch of terms. This is a big mess, right? To try to solve this is pretty messy, okay? But this is right. I mean, I boxed for you the 4 equations you need, and now it's just a matter of solving it all. By the way, you do need to get the rest of the H's, and I told you you can get them, so I'm just going to give them to you, okay? You get H1 because just to let you know, state 1 is going to be sat liquid, just to let you know, and it's going to be 10 kilopascals. So it turns out H1 is 191.83 kilojoules per kilogram. Okay. Anybody know how you get H2 if I gave you H1 there? Anybody remember that equation that you have to do for if you go from 1 to 2 and you have a pump? I think you got it, the VP2, but yes, the work of the pump, that's right. Remember, if you have a pump, whenever you see a pump, remember this equation, that the work of the pump is equal to the specific volume times the pressure difference, right? So you're going to use that equation to go from H1 to H2, because really what you have is H2 minus H1 is equal to the specific volume P2 minus P1, okay? So once I gave you H1, you can use that pump equation to get H2. Now that'll always be a very small difference between both sides of a pump. There won't be much. But if you do the analysis there, it turns out that H2 will be equal to 201.92 kilojoules per kilogram. Yeah.
Is like you find the pressure of 2 because it's going to be equal to
Yeah, what is the pressure at 2? What is the pressure at 2?
0.8.
No, because what happens when it leaves the pump 1 and goes to 2, and then it goes through to 9, right? Then it hits the mixing chamber and goes to 4. What's the pressure at 4? We should know that, right? 10. Well, doesn't it have to be also 10 at 2? How would it, if it was 0.8, what makes it pump up any higher, right? So it has to be 10 at state 2. So anyways, fill in some of these other things. Turns out state 3, some people might go, well, how do I know state 3? Turns out that state 3 pretty much has to be sat liquid because we're about ready to pump it. So we're going to pretty much make the assumption that it's sat liquid. And it's at a pressure there of 0.8 megapascals. So you can look that up, and you get around 721.11 kilojoules per kilogram. Okay, I'm just going to give you all the other H's that you know. Okay, so H3 is 721.11. Yeah.
0.8.
Yeah.
Okay.
0.8 megapascals. Yeah. Okay. And then to go down to H10. How do you get H10? Just anybody? It turns out to be 731.37. Oh yeah. Yeah, H10 is 10 MPa. So you get H10 from H3, right? You go from 3 to 10 using the pump, right? So it's the same thing as what we did from 1 to 2. You do the same analysis from 1 to 2 as you do 3 to 10. Yeah. Sure. H3, 721.11. So it doesn't go up much between 3 and 10. Okay? Now, and then let me give you 10, make sure. 10 is 731.37. How do I know 4 was 10? Because the boiler is at a constant pressure. That's what we always assume with Rankine cycle. And it says it enters the high pressure turbine at 10, so it must leave the boiler at 10 and must stay constant pressure 10. Yeah. Yes, yeah. The boiler does not increase the pressure. It just heats it up. 10 megapascals at 4, 10 megapascals at 5. 10 megapascals at 10, 10 megapascals at 9, 10 megapascals at 2. Well, 3 has 0.8 megapascals. 1 has 10 kilopascals. So there's actually 3 pressures. There's a high pressure, a low pressure, and a medium pressure. Oh, yeah. Okay, so how am I going to solve this? Okay, the way to really solve this, I thought when I looked at this all, I said, oh, I'm going to have to go to Excel. So I pulled out Excel. I made a spreadsheet. Here we go. Now, what I did on my spreadsheet is I filled in all the H's. Okay, I filled in all my values for H's. And then I left on the spreadsheet highlighted in yellow the unknowns. Okay, H4, H9, M dot is unknown, right? And so is Y, right? So I have 4 unknowns, right? And then what I did is I made equations here. Notice, remember we had work out? Well, I made an equation for it. I typed it in. I said, oh, here it is. Work out, D1 represents M dot, right? And each cell represents one of those variables. So I put them all in. The cells, each cell represents a variable there, and I put them all in. Let me scroll up if I can, so you can see that. You can see where I'm grabbing those variables if you can see that. I'm grabbing all those. So I did that for each one of them. I did that for work out. I did that for work in. Okay, there's the work in. I did them for all of them. Okay, well, Q in, Q out. Then I actually made the constraints. Remember, the network has to be 80,000 kilowatts. The network has to be 80,000 kilowatts. So I made an equation. This is a very simple equation because it's just B12 minus B13. Work out minus work in. Because I already have the expressions for work out and work in, so it's really easy then to just put that right there. So that made it easy. Okay? And then I also have analyzed both the open feed water heater, which is the mixing chamber, and I've analyzed that. I got that, the expressions for that. And then I've also got expressions for the closed feeder, and then I've got an overall first law analysis done. Okay? So I got them all together, I put them all in there, and then what I did is I said, okay, I'm going to pull up my solver and solve this thing. Okay? Now, when I did this with the solver, Excel solver is not super duper. Okay? It turns out that it needs a decent guess. Just does. Okay? If you give it nothing, I'll show you. It didn't work. I went here and I went to data solver. I popped up the solver. Okay, now the solver says set an objective, meaning you can set, I just made up an objective because I didn't really have one. I just wanted to solve it. I didn't want to like maximize anything or minimize anything. I just wanted to solve it. So I made it a made-up objective of maximizing cell D1, and cell D1 is the mass flow, whatever. Okay, so I made that up. But here's what I said. I said change the variable cells. The variable cells here are the ones I have highlighted. Okay, so the variable cells are the cells highlighted. Subject to the constraints are the ones down there at the bottom. So I've got the 4 constraints. And then what I did is I hit solve, and it just didn't work. It just said solver could not find a feasible solution. So that made me sad. But what I realized is that these 0 is not good enough. Basically it uses 0 initial guesses. And 0 just wasn't a good enough initial guess. So what I had to do with H4 is I said, you know what? H4, H9, H10, they're all pretty darn close. So I just kind of put in there 725 for each one in my, just to start it, just an initial guess on both of those, right?
Could you get away with 1?
So, no, probably not. And then here's the key one, M dot. I mean, you kind of have to go with something, but I found, I kind of just said, oh, let's try 40 maybe. And then Y, the fraction, I figured that typically it's a low. Y is usually 10 or 20%, so I decided to try 20%. And so you might have to play with this a little bit, and unfortunately, bad news, sometimes the solver gives you the wrong solution because there's actually multiple solutions here, okay? So that can happen, so you have to be careful. But anyway, so I went to the solver again with those initial guesses. I hit solve, and it gave me that, 56, 20, it's better, okay? Now it turns out that, look at H4 and H9. Those values are kind of off because they should be really close to H10. So that's not really the exact solution, but if I do this and I bring this back and say, 725 again, and I'll make this 725. I could iterate, but it's kind of clunky, I will admit. You take this to around 50. If you do that, throw my solver, let's see if I can get pretty close. This time I think I will. Yeah, I'm getting closer. That's pretty close. Yeah, it turns out that's really, really close. So it's probably okay. It's not the best way to do it. You might want to try, and remember too, I'm trying to optimize. Maybe I don't want to optimize. Maybe I want to figure out a different way of doing this. Maybe instead of doing this, maybe I want to minimize y. I don't know. You'd have to play with it a little bit and see. That didn't do much there. Have to play with it a little bit and see if we can find, a better solution. But it's getting pretty close. Okay. Anytime H4 and H9 come close to H10, you're really close. Unfortunately, in this, you're going to get multiple solutions. But this is really close. Okay. By the way, when I saw this problem worked out, one of the things they did to simplify is they just assumed H4 and H9 were equal to H10, and then that made life a lot easier because then you could do the analysis much quicker and didn't have to go through this. But I kind of wanted to show you this. Also, I want to mention one more thing. I feel like I should because it's very common software out there that we don't use because it's stinking expensive, but it's out there, and that is EASE. I should probably mention this to you here. EASE is engineering equation solver. Okay, and EASE can do this kind of stuff too. You can throw all your equations into EASE, and it can solve it. Now, why would you use EASE and not Excel? One, it has some better solving routines, because Excel solver is not the greatest. Okay, but here's the really cool thing about EASE. It has all the thermodynamic data built in. So what you can do with EASE is you can say, give me the enthalpy of steam at 10 megapascals, 550 degrees Celsius. You don't have to look up anything. You just plug it in, and EASE gives you the numbers. So you never need tables with EASE. You never need any of that. It does all that for you automatically. So it saves a ton of time. Okay. Unfortunately, I think it's kind of expensive. I think the student version is like $100, and they used to package it with the textbook, but then they stopped doing that, and so I stopped using it because it's expensive. But I thought I'd show you that because EASE is really neat. It can look up all the data for you. It does a lot of solutions and things like that. It has very powerful solving. Really nice system. Okay. So anyways, I wanted to show that to you and at least kind of give you a technique. The key thing I want you to recognize is being able to write the first law of the whole system and also of the mixing chambers and things like that so we can analyze this.